This is an amplifier circuit for the Electronics 325 course at Texas A&M. This is a three-stage amplifier with a final stage that is composed of two parallel transistors. The first and second stages are common emitter stages. The final stage is a common collector stage. The input comes in at this point on the board, passes through a coupling capacitor, and after amplification of the common emitter, the signal travels along the orange wire through another coupling capacitor. The second stage is amplified further through a second signal wire, through a third coupling transistor or a coupling capacitor, into the final stage, which is common collector, again with the parallel transistors. And then the signal passes out from this orange line here through this coupling capacitor to the output here. The test assembly is made up of oscilloscope lines only on the signal input. This is the channel 1 input, and then channel 2 is referenced here at the end on the oscilloscope. Now this has been powered on for a few minutes without a signal coming in, so I can check the transistors manually to make sure they're not dissipating too much heat. This one here is by far the warmest, but is obviously not too hot to touch. And I've included test numbers for it in my report to show that it is not dissipating too much energy. The purpose of the two transistors is, of course, to divide the load between them, which ensures that they will not be damaged, because the load by itself is not too much for even one transistor. It just passes very close to the performance numbers of the transistor. So we're going to turn on the input signal now. And do an auto set here on the oscilloscope. Which will demonstrate that the waves themselves are being amplified. Let's bring this one up here. Place them on top of each other so that you can see. Alright, so both waves are laying on top of each other, but you can see that the peak-to-peak of the input signal is being measured as approximately 46 millivolts, and the channel 2 output is approximately 960 millivolts, which is sufficient for a 20 volts per volt amplification. And then for a harmonic distortion analysis, look at the Fourier transform here. I'm going to zoom back in until we see the primary harmonic, or the primary fundamental frequency. And then we'll place the cursors on each of the peaks. So the first cursor here is on the fundamental frequency, as you can see here. The second cursor is on the first harmonic, 20 kilohertz. And as you can see right now, the difference between the two is around 38 to 39 decibels, varying up and down a little bit. This indicates that this is a well reproduced waveform with minimal distortion, because the sine wave is what's coming in. And I'll zoom back in on the wave here, and let's make the output show very cleanly there. As you can see, this is a nice clean sine wave output. And in this circuit, we had to reduce the input gain, because when I recalculated the input impedance, the input impedance was too low. It was approximately 93K. So I removed the bypass capacitor and resistor that we were using to adjust the gain of the first stage, and adjusted the gain of the second stage using this potentiometer, which is in series with this bypass capacitor, which bypasses the emitter resistor here, and raised up the gain on the second stage to give the gain numbers that we're looking for. So at this point, the gain is approximately 2 in the first stage and approximately 10 in the second stage. There is no appreciable gain in the third stage. It provides a gain of approximately 0.95. And all of these fall within the specifications of high input impedance, 20 volts per volt amplification, and low signal distortion for the 325 amplifier project in Dr. Jose Silva's class. Thank you.